first part will be, as I said before, on energy resources. So again, just as a quick reminder, make sure to, if you have any question whatsoever, even the tiniest of detail, just ask in the Teams Q&A, because it's a really good way for me to see if you guys are following the lesson, and it's a good way for us to add more content to the lesson, because obviously we can then publish your question if it's interesting, and other students might be able to see the published questions, and maybe it was a question they were thinking of asking. So really don't hesitate to ask any questions in this Teams Q&A. So what is energy? Energy is basically it's kind of it's a storage of energy. Basically, you've got a certain amount of energy that can be used to do work. So it's basically a resource that you can use to do all the activities that you do throughout the day. So just as we take in energy in our food, all the activities we do as human beings costs us joules. What do we mean by joules? Joules is the unit of energy. Even processes as simple as breathing or blinking require a certain amount of energy. If you imagine you have a certain amount of energy to start the day, just living, just breathing during movement costs us energy. So the energy will go down, 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 down. If the energy goes down, you might feel tired, you might feel exhausted, so you eat a bit of food to gain some energy. So by taking in food, you take in some energy. You know that food has a certain amount of calories. Basically, calories is a measure, is also a measure of energy. So your tank of energy goes up, 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 up. So that's why there's this balance between what you eat, which increases the energy, and what you spend on activities, which decreases the energy. Really good question in the chat. When is lunch? Lunch is at 12:30. So running for 30 minutes, for example, we use as much as 1,100 to 2,200 joules in energy. So physical activities will use quite a lot of energy. A good question that I might ask you guys is, what do you think is the organ that uses the most energy in the body? There's one specific organ or part of the body that uses the most energy throughout the day. It uses as much as, I think, 20, maybe 25%. I think it's 20% of the calories you eat, and it's the brain. The brain obviously is basically the control tower of your body, and is the organ, is the part of the body that uses the most energy. So that's why it's really important to take in some food, because if you don't, then your brain might not work as well, which isn't ideal, of course. Yeah, the brain. So again, see, this is an example where there's this delay in the live. I see your answers after I've asked quite a long time after I've asked a question, which is unfortunate. But please do answer the questions in the chat, even if I see them after I've given the answer, because I can see if you've understood or not. And it keeps the interactiveness between us. Okay, so how much energy do different activities use? Have a guess at how many joules these different activities take. So, we already know about running that uses 1,100 to 2,200 joules. But how about doing yoga, for example? Well, it's estimated that doing yoga, and we can estimate how much energy is used during yoga and during boxing, for example, just by seeing how the body reacts to those different activities, how the amount of energy our muscles, our brains, or just any part of our body uses to do these activities. You might think of an analogy would be, for example, a car. A car takes fuel. You need to add fuel in the car to be able to use it to drive forward. So that's an example. In our case, we eat food that we can then use to do movement. In the case of the car, it uses fuel to be used to drive forward, drive backwards, and so you use that energy to convert it to another form of energy. So the point of energy is to take a certain form initially and convert it into another form. For example, the energy that's stored in our food isn't very useful in food. It's when we can use the energy in our food to do movement. That's when it's useful. So you go from chemical energy in the food into kinetic energy, my movements. Okay, so people say around 500 joules, maybe 8,000 for boxing, maybe 3,000, 4,000 for boxing. Okay, let's look at what the slides say. So half an hour of yoga burns around 500 joules of energy, and an hour of boxing burns around 800 joules of boxing. Of course, these are really rough estimates. This depends a lot on the intensity of the activity and depends on the person. From one person to another, you might burn more or less energy. For example, a person that might be a bit more overweight and has a different body type will burn a different amount of energy to someone that's really fit and has a very fast metabolism, for example. So yeah, those are really rough estimates, but it's a good way to see how energy is used in sport. What is the best sport to burn as many joules as possible? Well, there's quite a few. And again, it depends on the intensity. That's why there's no one solution to burn as many joules as possible. But in general, I know swimming is a really good sport to burn as many calories as possible because it uses all parts of the body and it doesn't damage your knees like running does. So it's quite good. Okay, so now we can ask, how much energy does my house use? We know that for our bodies, there's a certain amount of energy we use, etc., etc. But how about a house? A house uses energy to convert it into useful energy. For example, here I use my computer, so it's energy in the form of electricity that goes to my computer. I use Wi-Fi, I use lights. Those all use energy. So how can we calculate how much energy a house uses? So if a house uses a kilowatt hour of energy, it has transferred 1,000 joules a second consistently for an hour. So what does that mean? The amount of energy a home uses is measured in kilowatt hours. A kilowatt hour is simply a kilowatt of energy transferred consistently for an hour. Okay, that's the definition you need to know. A kilowatt of energy transferred consistently for an hour. So we use the letters K, W, H, kilowatt hour. Okay, so what is a kilowatt? A kilowatt is 1,000 watts. We know that kilo is for 1,000, for example, kilogram is 1,000 grams. So kilowatt is 1,000 watts. Now, what is a watt? What is the unit watts, this W? Well, it's a certain amount of energy per second. We say that it's a power. The unit of power are watts. So a kilowatt is basically 1,000 joules per second. So who created the word kilowatt hour and when was it made? That's a really good question. I don't really know who introduced it. It's just that it was a useful unit to measure the energy used in a house. So a kilowatt is 1,000 watts. That's the first step. Then what is watts? Watts are the units of power. We know that power is a certain amount of energy per second. Energy is measured in joules and second obviously is measured in seconds. It's basically an amount of energy divided by a certain amount of time. So that's why we use joules per second. Okay, and then what is an hour? 1 hour is basically, we know that it's 3,600 seconds. We know that there's 60 seconds in 1 minute and there's 60 minutes in 1 hour. So to find the number of seconds in 1 hour, you need to do 60 times 60, which is 3,600. So basically, 1 kilowatt hour is 1 times 1,000 joules per second multiplied by 3,600 seconds. So what did I do here? I just replaced kilowatts with its definitions definition in joules per second, and I replaced an hour with its with the number of seconds that are in an hour. An hour is equivalent to 3,600 seconds. Okay, so why am I doing this? I want to have a rough idea of what kilowatts hour is in joules. So basically, kilowatts hour is a measure of energy. Energy is a certain amount of power times a certain amount of time. Here, the amount of power is kilowatts, and the amount of time is hours. So we can convert this unit of kilowatts hour into units of joules, because we know that kilowatt hour is a unit of energy, and we know that joules is a unit of energy. So how do we convert from one to the other? Well, that's what I'm doing here. 1 times 1,000 times 3,600. Okay, so if you look at the units, you have seconds divided by seconds. So when you have something divided by that same thing, it cancels out. So the seconds cancel out. And you have 1,000 times 3,600. There's a really good answer in the chat. The answer would be 3,600,000 joules. Why joules? Because that's the unit that remains at the end. So basically, 1 kilowatt hour is equivalent to 3,600,000 joules. Okay, so why do we introduce this? Well, it's a useful unit to use because houses use a big amount of energy. So instead of calculating the energy of millions of joules, we use kilowatt hour. Kilowatt hour is a very big unit, as you can see. It's above 3 million joules. So instead of saying a house uses 3,600,000 joules, we say that it just uses 1 kilowatt hour. So it's easier to it's just easier to use to have smaller numbers. How much energy does my house use? The cost of running a home can calculated using this simple formula. The cost is equal to the power times the hours times the price per kilowatt hour. So the power times the hours. What is power times hours? We know that kilowatts times hours is simply energy in kilowatt hours. Energy in kilowatt hours. We saw before that 1 kilowatt hour is equivalent to a certain amount of power in kilowatts multiplied by a certain amount of time in hours. So power times time in kilowatts and in hours is equivalent to the energy in kilowatt hours. Now, if you multiply the energy in kilowatt hours times the price per kilowatt hours, that should give you just the price. Just like, for example, the number of apples times the price per apple is the total cost of multiple apples. If I buy 2 apples and each apple costs £1, I know that I'd be paying £2, just 2 times 1. So it's the same here. A certain amount of energy times the price per this amount of energy gives you the total price. You can see this using the units as well. The price is per kilowatt hour. What do I mean by per kilowatt hour? Is basically 1 divided by kilowatt hour. Well, it's not 1 because it's a certain it's a certain price in pounds. So the price per kilowatt hour is the number of pounds per kilowatt hour. And if you multiply this by the energy in kilowatt hour, the two cancel out and you just get the number of pounds in the end, which is what you want for the cost. Okay. So imagine you had been put in charge of calculating how much money a home spends on energy. We remind ourselves that the cost in pounds is the power in kilowatt hours times the time the house is used in hours times the price, so in pounds per kilowatt hours. So imagine they've used 30 kilowatts of energy in 24 hours and the energy company charges 20p per kilowatt hour. How much does it cost to run this house? So you've got the power, 30 kilowatts, so that's this. You've got the amount of time. They've used all 24 hours of the day, so you've got the time in hours, which is 24. And you know that it's 20p per kilowatt hour. So you've got the price here as well. So you've got all you need to find the cost of energy in this particular house. So how much would the homeowners need to send the energy company? How much do they need to pay? Well, we know that it's they use oh, it's the wrong way. It should be 30 kilowatts times 24 hours to just switch the units. Let me check if that's correct. Yeah, 30 kilowatts. So we know that we use 30 kilowatts for 24 hours. So the amount of energy used is 720 kilowatts hour. Okay, now we've got the energy. This is essentially what we calculated is this here. The power times the time. Power times the time is energy in kilowatts hour. Now, all we need to do is multiply that energy times the price per kilowatt hour. We know that the price per kilowatt hour is 20p. So essentially here they forgot something that's quite important, is that the price per kilowatt hour is 20p per kilowatt hour. So you've got 20p per kilowatt hour, so the kilowatt hour cancelled out. You've got it above and below. It's as if you multiply by 2, then divide by 2, they just cancel out. Multiply by 10, then divide by 10, they just cancel out. So here you multiply by kilowatt hour and divide by kilowatt hour, so they cancel out. And all you're left with is the units of p. So multiplying the two, you get 14,400 pences. How do you convert this into pounds? Well, is you divide by 100 and you get 144 pounds. Okay, so that's quite a useful little formula to remember. The cost of running a house is the amount of power the house uses times the amount of time it uses that power for, because obviously it will change if you use only for an hour compared to if you use for 20 hours. So if you double the time, you will obviously double the cost. And then obviously it also depends on how much 1 kilowatt hour costs. If it costs £1, does it cost 20p? Does it cost £2? So that depends on how much the energy company charges. Okay, so how much do different devices use? So imagine your 20p per kilowatt hour house contained these devices. How much would it cost to run these devices for an hour? So imagine there's a toaster, a laptop, and a coffee maker. Okay, so we remind ourselves that the cost is power times time times the price per kilowatt hour. A watt is a unit equal to 1 joule per second, and a kilowatt hour is a kilowatt of energy transferred for an hour. Okay, let me check if I've added a slide. Should I add maybe little slide? Okay, while I think about how to add a little slide, can you try to find how much would it cost to run a toaster, to run a laptop, and to run a coffee maker for an hour? You knowing that it's 20p per kilowatt hour. Okay, try to answer this while I'm just add a little slide here. Okay, there you go. So 800 watts, 50 watts, and 1000 watts. So we have 800 watts toaster, 50 watts laptop, and 1000 watts coffee maker. Okay, so 800 watt toaster. First of all, we need to convert the watts into kilowatts. Remember that we need to have the right units. So what is 80 watts in kilowatts? Well, you need to divide by 1000. So it would be 0.080 kilowatts, or simply 0.08 kilowatts. Okay, what's 50 watts in kilowatts? Well, 50 divided by 1000 would be 0.05 kilowatts. And 1000 watts is simply 1 kilowatt. Okay, that's the first step. Convert the watts into kilowatts. Then we know that we run the each device for an hour. So how much energy do each of these use? They use 0.08 kilowatt hour, because we simply multiply by an hour. So we go from a kilowatt to kilowatt hour because we simply multiply by an hour. So this is 0.05 kilowatt hour, and this is 1 kilowatt hour. All we did was use for 1 hour. Okay, now we know that it's 20p per kilowatt hour. That is how much the energy company charges for 1 kilowatt hour. So we need to multiply by 20p per kilowatt hour. So to find the price, we do 0.08 times 20p, which is equal to, let me see, 0.16p. Okay, the laptop uses 0.05 kilowatt hour, so it will cost 0.05 multiplied by 20p, because it's 20p per kilowatt hour, which gives us 0.1p. And finally, a 1000 watt coffee maker would be 1 multiplied by 20p, which is equal to simply 20p. Oh, did I do a mistake? Oh, yeah, sorry. Here I did 80, but it's 800 watts. My bad. There you go, 0.8. So it's 0.8 kilowatt hour, 0.8 here, so it's 1.6p. I think that's the only mistake I made. Then it's a 50 watt laptop, and then it's a 1000 watt coffee maker. Okay, so here all we did was use the standard formula, which is the number of kilowatts times the number of hours times the cost per kilowatt hour to find the total cost. So a 800 watt toaster for an hour uses 1.6p of energy. A 50 watt laptop used for an hour uses 0.1p of energy. And a 1000 watt coffee maker used for an hour uses 20p of energy. It's simply using kilowatts times hours times price per kilowatt hour. Let me know if I made any other mistakes. Thank you to Victoria and Niam for pointing this mistake out. So where do we get our energy? It's all fun and games to have a certain amount of energy that you can use, but where do we actually get it from? Like, is it from renewable sources? Is it from fossil fuels? Is it from fuel? Is it from something else? There's many different type sources of energy. Okay, so an energy resource is something with stored energy that can be released in a useful way. So we get electricity from a combination of resources. Each has advantages and disadvantages. So renewable energy, on the one hand, is energy that can be replaced. It can be reused over and over again. So this is the most sustainable form of energy because it doesn't lead to any waste, and you can just reuse and recycle. It's energy that won't run out. You can just use it again and again and again. And it's renewable, so it's sustainable. It doesn't cause any waste. And then on the other hand, there's non-renewable energy. This is energy that can't be replaced. Basically, once it's used, that's it, it's gone. And it's energy that will run out. Okay, in the chat, can you give me examples of renewable energies and non-renewable energies? For example, one big example of non-renewable energy is fossil fuels. Can you try to give me examples of renewable and non-renewable energies? Okay, solar power is one of them. Nuclear energy, wind energy is renewable energy. Tidal energy, really good. Geothermal. Nuclear energy for non-renewable, well done. Solar wind waves, you would just say solar power, solar energy. Oil for non-renewable, coal for non-renewable, wind turbines and waves for renewable, natural gas for non-renewable. Okay, so then you just repeat yourself, but petrol for non-renewable again. Okay, really good. Let's look at some examples given in the notes. So one big part of the non-renewable energy is fossil fuels. It's non-renewable energy resources formed from an ancient remains of ancient plants or animals. It's basically plants or animals that have been like decomposed and made this kind of oil that can be used as energy. It basically has it's a store of an enormous amount of energy, which, when used correctly, can really give a big amount of energy that can be used in a useful way. So there's quite a few types of renewable energy sources. So here we're considering renewable. So you've got solar power, you've got wind power, water power, geothermal power, and biomass power. Those are basically the 5 main ones. So each have their own advantages and disadvantages. The advantages of solar power is that there's no pollution. Basically, all you do is use the light from the sun to convert into electricity using solar panels. And it can be used in rural areas. What's good as well is that it can be used over really large surfaces. So it it's quite useful in that sense because it can cover a large surface, can be put on roofs to convert solar power into electricity. The disadvantages is that they're quite expensive. Solar panels are quite expensive, and it's of course, only efficient during the day. Okay, what's the advantages of wind power? It causes very little pollution, and it represents an income for land owners. Of course, by putting a wind turbine on their lands, it's an income for them because it produces energy which they can then sell. The disadvantages is that the wind is quite inconsistent, similar to the solar power, where if you have no lights, then there's no energy. In the case of wind power, if you have no wind, then that produces no energy. Another issue is that it's quite noisy, and something that you might forget is that, of course, wind turbines, they affect the winds. And if they affect the wind, it might disturb the flight of birds, which is also something that's not ideal. But yeah, they're quite noisy. I don't know if you've ever been next to a wind turbine, but it makes a lot of noise. They're obviously those huge structures, so if they move at a certain speed, they will cause some noise. Okay, how about water power? Well, waves are always very regular, so you should get a roughly regular production of energy because they come at a regular rate, and it's often the same. It's quite consistent. It's also quite safe. However, it's really difficult to transport energy from the sea to the shore. Something that you need to remember is that there's always a certain efficiency. What do I mean by efficiency is how much of the incoming energy is converted into useful energy. How much of the incoming solar power is converted into electricity. How much of the incoming wind power is converted into electricity. Well, for water power, it's quite difficult to have a high efficiency. Basically, despite having high energy waves, it's quite difficult to have an efficient transition from this water energy into electricity or another form of useful energy. Okay, then there's two more rogue ones, geothermal and biomass power. Basically, they cause little pollution and a constant supply because it's from volcanoes. Obviously, it's quite risky to stay near volcanoes, and it's only in certain places where there are actually volcanoes or those really warm, warm soil, they can use geothermal power, but it can be quite useful. And same for biomass. It basically uses the waste of food. It's quite cheap, but it does release greenhouse gases. And we know that greenhouse gases causes the warming up of the earth, which isn't ideal. Now, some non-renewable energy. So there are two main ones. I've introduced the fossil fuels before, for example, coal, crude oil, and natural gas. Obviously, they're all quite cheap. They're all easy to locate in the earth. They can be easily transported, and we know how to get them. So they have really good advantages of being cheap and easy to use. However, there are really big disadvantages linked to fossil fuels. They cause a high level of pollution. So what do I mean by pollution is that by using fossil fuels, what's released is also gas that will pollute our atmosphere. Oil can also cause environmental damage. I don't know if you've seen some boats carrying fossil fuels that then, if they crash, will basically spill all their oil in the water, which can have devastating consequences on the environment. And another main issue is that, of course, non-renewable energy, as the name suggests, is non-renewable. So once you've used it, that's it. It won't come back unless you wait thousands of years for it to naturally come back by itself. Once you run out, and that's it. You don't have any more energy. And we are close to running out of fossil fuels. That's why we need to find alternatives, because if you don't have fossil fuels, which yes are very cheap, very easy to use, if you don't have that form of energy anymore, then obviously it becomes useless because there's no more of that source of energy. Another really big form of non-renewable energy is nuclear power. It's very efficient. What do I mean by very efficient? Is that it has a high efficiency from the incoming energy from the nuclear reactions into the outcoming electrical energy. It also has very low carbon emissions. However, despite having very low carbon emissions, it's still highly polluting. Why is it highly polluting? That's because nuclear waste is highly radioactive. Basically, what is nuclear power? Is when you take, for example, an atom of uranium, you smash a particle into it, which breaks the atom. When it breaks, it releases a massive amount of energy. However, these the atoms that stay after that reaction are highly radioactive, and radioactive waste can really damage the environment. So that's why people need to be very careful in nuclear power stations, because if any nuclear waste goes outside the safe environment of the nuclear power station, it might have devastating impacts on the environment, just like we saw in Chernobyl, where the nuclear power station exploded and the whole area was extremely dangerous to live in for many, many years. Okay, so let's try a little slider. Let's see if... Okay, why does this not work? Okay, my computer just froze. Give me a second. Okay. It's a bit annoying. Try this again. Okay, so this doesn't work. Okay, really sorry. For some reason, the sliders don't work. Okay, that's quite annoying. Okay, I'll make new sliders during the lunch break, because apparently this doesn't work. So hopefully we can go through as much content as possible before the lunch break, and I'll do a few Slido interactions during the lunch break so that we can use for the last part of the lesson. Maybe I'll do a little quiz so that I include everything that was that we looked at during the lesson, and I can just do that at the end of the lesson. Really sorry, I don't know why these interactions don't work, but that's fine. So forget about Slido for a second, and we'll just carry on with the lesson. Okay, so basically what we saw so far is a really brief summary on energy resources and the cost of energy. So that was the first part of our lesson. Unfortunately, I don't have any past paper questions on energy, as it's a really broad subject. So you'll see that next year you'll go into more details as to what each form of energy is and how we can actually calculate how to transfer from one to the other. So I don't have any questions, but the main thing is that you understand the main concepts and have an idea of the theory for now, so that next year you'll be able to do the practice questions. Okay, so that was the first part of this lesson. Let's now go to the second part, which is on sound. Okay, so what is a sound wave? Basically, a sound wave is emitted whenever an object vibrates. We say that it produces sound. So, what is a vibration? A vibration, for example, if I do this with my hand, that's a vibration. It's a back and forth motion that repeats itself. It can be very slow, that's a vibration, very slow and very large, or it can be very quick and very narrow. So vibrations can vary in amplitude and vary in speed. So that's the two main things that you need to know for now, is that vibrations can change in amplitude and change in speed. We'll see what we mean by speed later on. That's why I put it in quotation marks. Is do we mean the speed of the vibration or the speed of the propagations? Those are two different things. The main thing for now is that you know that it can change in amplitude. It can be very wide, or it can be more narrow, and it can be faster, or it can be slower. So vibration is just a back and forth motion that repeats. Okay, these sound waves travel as longitudinal waves through the particles that make up the matter. Oh, sorry, I need to remove this. So what is a longitudinal wave? Is when the vibration is in the same direction as the wave. Okay, so that's let's do a brief explanation of what a longitudinal wave is. The opposite of the longitudinal wave is the transverse waves. So there are essentially two types of waves, transverse waves and longitudinal waves. Transverse waves are easier to understand. For example, if I attach a rope to the wall and I attach one end of the rope to a wall and I hold the other end in my hand. If I just do an up and down motion, there will be a wave propagating through the rope to the wall. Obviously, if I do this motion, the rope will go up and down and it will propagate towards the wall. That's what we call a transverse wave. Basically, the motion of my hand is up and down. I make the rope vibrate up and down to produce this wave, but the wave propagates horizontally towards the wall. You see how the vibration is up and down, so it's vertical. However, the propagation is horizontal towards the wall. So that's what we mean by a transverse wave. It's where the oscillation, the vibration, is perpendicular to the propagation of the wave. It's the same for a water wave. A water wave, basically, if you look at the surface of water, waves oscillate up and down. It's basically you see the wave go up and then go down, up and down, and up and down. However, that's the direction of oscillation, is the direction of the vibration of the wave. But the direction of the wave itself, we know that waves move along the water. For example, when you go surfing, the wave doesn't just stay still, it goes towards the shore, so it goes horizontally. So despite the vibration being up and down, the wave propagates horizontally. So that's another example of a transverse wave. So example, water waves. So transverse waves is when the vibration is perpendicular to the direction of the wave. So now, what's the opposite? The opposite is longitudinal waves. Longitudinal waves is essentially when the vibration is in the same direction as the wave. And that's the case of sound waves. Basically, sound waves, when I speak, what happens? What happens is that obviously my vocal cords vibrate. When my vocal cords vibrate, the air in front of my mouth will vibrate as well. And it vibrates in the direction of the wave. For example, if I speak towards my computer, the air vibrates back and forth towards my computer. Maybe it's easier if I speak this way. For example, if I speak towards my wall this way, the air particles will vibrate back and forth in this direction, but I also speak in this direction. So the sound wave will also propagate in this direction. So basically, the vibrations are back and forth, but also propagate in that same direction. That's what we mean by a longitudinal wave. It's when the vibration is in the same direction as the wave. So there's two different types of waves. Transverse, when the vibration is perpendicular to the propagation, and longitudinal, where the vibration is in the same direction as the wave. In the case of sound waves are longitudinal waves. The first break will be in 10-15 minutes. Okay, so sound can travel through solids, liquids, and gases. Basically, sounds can travel through any kind of matter. You might think at first that sound only propagates through air, but that would be incorrect. For example, even in water, you can hear sounds. And funnily enough, sound can also propagate through solids. For example, the speed of sound in a solid is much quicker than the speed of sound in air. That's because in solids, obviously, density is much bigger, particles is much closer together. So if they vibrate, the propagation will be much more efficient, and it will propagate through the solid much more quickly than it would through a gas. So essentially, the way a sound wave propagates is the particles of the matter will start vibrating, will start oscillating, and they will basically transfer that motion by hitting other particles. And as they hit other particles, which will then hit another particle, that's how the sound wave propagates, is through particle-particle collisions, and it will propagate forward. Okay, I've got this question later on, so I'll skip it for now. Okay, so ultrasounds are waves with very high frequency.